fluid dynamics for the interview preparation. So, what is fluid dynamics? Fluid dynamics is basically a study of the fluid concerning about the cause of the motion. What causes the fluid to move, fluid to flow? So the reasons may be the pressure difference or gravitational difference. Uh, this can be the reason. That means there is a potential difference. Okay, potential difference function is also there. That is why the stream function is there. Okay. So the main question we ask in the fluid dynamics is, why does the fluid flow? Okay, and in this fluid dynamics, the essentially specific law is used here. That is Newton's second law. Newton's second law is nothing but the change in linear momentum with respect to the time, which is equal to the force. Okay. So let's see what is written here. Okay. So what is the meaning of conservation of momentum? If it is conserved, what does it change with respect to the time? Okay, we will see that here. So Newton's second law is nothing but the change in momentum, linear momentum with respect to the force. But this is true only for the solid bodies. Uh, in solid bodies, we take linear momentum, that is m times v. That is the v is the average velocity. Okay, so force is equal to change in momentum using the average velocity. And here for solids, the mass is constant because the mass doesn't change in time. It is same. So that is why, but the velocity changes. That's why dv by dt, we get the ma, mass times acceleration. While for the fluid, the mass changes with respect to time. For example, in the rocket propulsion, with the propulsion, the fuel level reduces, thus the overall weight of the body reduces. In that case, the mass changes. In that case, we use mass flow rate. So F is equal to m dot v, mass flow rate is used. And mass flow rate is nothing but density times the discharge. Okay, so conservation of momentum means the uh, the force is not, and the overall the net force is basically zero of the body. That means the body moves, the energy is conserved inside the body. So what doesn't change? The momentum doesn't change with respect to the time. If P is conserved, how about F external? That means if P is conserved, that means dP by dt is equal to 0. And that means the F external will be 0. What kind of external force are involved here? That means the net external, not just on F external, the net external force will be 0 when the momentum is conserved. What kind of external force are involved here? So the external force acting on the fluids are gravity force, pressure force, viscous force, turbulent force, compressibility force. We will see that later. Which is input and output here for F external or momentum? Give examples. So generally F external is the input and momentum is the output, but this can sometimes change. In some cases the change in momentum can be the input, and for external force can be the output, like in jet force on turbine. Jet force which creates momentum on the turbine blades, and that in return creates the force inside the turbine. So in this case the momentum is the input and force is the output. So this can happen. And as you can see from the picture, there are three important equations which govern the fluid dynamics. First one is the Euler equation, second is the Navier-Stokes equation, and third is the Reynolds equation. So in Euler equation and Bernoulli equation, two forces are basically considered, that are gravity force and pressure force. In Navier-Stokes equation, we consider gravity force, pressure force, and viscous force. And for the Reynolds equation, gravity, pressure, viscous, and turbulent force are considered. So now let's see about the Euler equation. So Euler equation is a relation between velocity, pressure, density of a moving ideal fluid. Ideal fluid means it is incompressible and it is inviscid. That means incompressible means the density doesn't change with respect to the time, or any other quantity or pressure. Inviscid means the viscosity is zero. Okay. Uh, so the Euler equation is a relation between the velocity, pressure, density of a moving ideal fluid in a steady flow. Steady flow means the velocity doesn't change with respect to the time. It is basically based upon the Newton's second law, which states that if the rate of change of linear momentum is zero, that means if the linear momentum is conserved, that is dp by dt is equal to zero, then the external force is zero. As I said earlier, conservation of momentum means the dp by dt is equal to zero. That means the external force is zero. The net external force is zero. So in a ideal moving fluid, the net external force is zero. That means the external forces due to the pressure, due to the gravity, and due to the kinematic velocity, then these are basically external forces, and the total external force will be equal to zero. Okay, so the Euler equation is nothing but dp, change in pressure, divided by density plus gravity times the change in datum or the height plus velocity times the change in velocity. This total is equal to zero. This equation is about the motion of the fluid. Okay, this is the equation for motion, and it is equal to zero because the net force is zero because because in this equation the momentum is conserved. This equation is calculated on the same streamline. That means if you choose a particular streamline, and all the calculations are done on the particular streamline in different sessions. So what are the forces involved here? Pressure force and gravity force and inertia force. That is inertia force of the fluid. So dp by rho is basically the inertia force, g by dz is gravity force, v by dv is basically the inertia force. Used to this inertia force is the force which breaks the resting position of the fluid. When this force is applied, the fluid moves. Okay. So what are the assumptions in the Euler equation? So the assumptions are that the flow is steady, that means the velocity doesn't change with respect to time. The fluid inviscid, that means the viscosity is zero. And it is incompressible, that means the density doesn't change. And it is irrotational, that means the fluid particles or the elements, the angular velocity of those elements, the net angular velocity of the element is zero. It means the fluid doesn't rotate. Okay. So let's see what is written here. So this is the another form of Euler equation. You will see that later. So this is equation for motional energy. It is for motion. This is equation equal to the constant of 0, 0. Why? Because the net the conservation of momentum, the linear conservation of momentum is equal to 0. That's why the external force is 0. So the expression is basically about the external force, which is equal to 0. So what does the Euler equation tells us? So Euler equation is basically the relation between the pressure, density, and velocity of the moving ideal fluid in the steady flow. This equation calculated for same streamline or path line, and why? It is for the same streamline because only in the streamline the velocity at all the sections are same. That means it's a velocity doesn't in the streamline, the velocity doesn't change with respect to the time. That means at all the time at a particular position the velocity is same. Okay. So next, forces. So dp by rho is pressure force. This is the gravity force. This is the inertia force. Inertia force is equals to the break the inertia force to create the motion. Okay. And as I have seen, assumptions, which kind of flow is this? It is a steady flow. Which fluid? Ideal fluid. That means it is incompressible as well as inviscid. Is it rotational? No, it is irrotational. Okay. Now let's go to the Bernoulli equation. So what is Bernoulli equation? Bernoulli equation, it is a relation between the pressure, velocity, and elevation in moving ideal fluid. where the fluid is incompressible and inviscid and the flow is steady. It's same as the Euler equation. This equation or theorem states that the total mechanical energy of the flowing fluid, compressing of the pressure energy of the fluid, gravitational potential energy, and kinetic energy of the moving fluid is constant. So, what is Bernoulli equation? It is basically the relation between the pressure, velocity, and gravity of the ideal moving fluid in a steady flow. What does this theorem states is that the total mechanical energy of the fluid is constant. That's it. It implies if the fluid flow through the horizontal pipe, that is, there is no change in the height, that means there is no change in potential energy, rho p, rho gh, is the change in rho gh is 0, that means there is no height difference, that's why there is no change in potential energy. Then decrease in pressure is associated with the increase in the velocity. Wherever there is increase in velocity, the pressure decreases. As from the continuity equation, we know that increase in velocity is basically decrease in area. We will see this, we will understand this relation later. Okay, so let's see what is written here. So this is the form of Bernoulli equation. We will see that later. So this is equation for motion energy. This is equation for energy, because the total mechanical energy of the fluid is constant. The equation equals to the constant. And this is calculated on the same streamline, because at streamline the velocity doesn't change with respect to the time at particular section. How to find Bernoulli equation from Euler equation? So, we just missed Bernoulli equation or theorem is the principle of energy conservation of the ideal fluid in steady flow. It is the energy conservation. The energy is conserved. That means the energy doesn't change. It means energy is constant in the flow. So Bernoulli equation is obtained through integrating the Euler equation. So let's first consider for the ideal flow. Ideal flow in which the viscosity is 0. So we will see for the specific energy equation form that we will take the Euler equation, which is equal to 0, as the net force is external force is 0, and between the two sections of the flow we just integrate it. After integration we get this final equation, P by rho plus G by Z plus V square by 2 is equal to constant. This is basically the specific energy form equation, which means this equation is already divided by mass. If we multiply by mass, we get such an equation, mgz plus mv square by 2. You can see that mv square by 2 is nothing but the kinetic energy, mvz is nothing but the gravity potential energy, and this is nothing but the pressure energy. All this energy is basically equal to a constant. So the specific energy nothing but this whole energy form divided by the mass. So this is one form of equation. So how is it an energy equation? So this is from this derivation, this equation is a specific energy equation. Okay. So which is the pressure head, kinetic head, and dead head? So we will see that. So here's the head form. So when this equation is divided by g, gravity, we get such a form. So you see, we divide by g, we get p by rho g plus z plus v square by 2g is equal to constant. When we divide by g, we get a head form, and all these units are in meters. Z is the height, is in meter. This representation is basically in meter. Everything in meter. And this expression p by rho g is basically the pressure head. Z is the datum head. V square by 2g is the kinetic head. Okay. So if we have a tank like this and we have an exit here, if you want to calculate the velocity here with respect to the datum head, so we can find the velocity as v square by 2g is equal to c, and v is equal to root 2gc. And if you want to calculate the power is nothing but the pressure times the discharge. That is, pressure is rho gz times q, okay, which is also the potential energy equation, but nothing to worry. So what is written here? Let's see for the ideal flow. So in this case we use inviscid flow, that is viscosity 0, energy conservation term, stored form of energy, and This part of the equation is called energy gradient line. Okay, we will see that in coming equation. So, how is pressure related to area from the Bernoulli equation? What is the role of continuity equation? So let's see. How is the pressure related to the area from Bernoulli equation? So as we know that pressure is equal to force by area. If the area decreases, what happens to the pressure? Simply with this equation, we cannot say that decrease in area is maximum. Maximum is in pressure. It's not so. But the other way, the pressure force is equal to area times pressure. Yes, increase in area is also increasing pressure force. It is directly proportional. But this equation is not inversely proportional with respect to the area. But from 1D continuity equation, we know that discharge in both the sections are same. That means this equation is same. And from this way, if we consider the incompressible fluid, the is same. And this we remind with this expression. That means area and velocities are inversely proportional. That means increase in area is decrease in velocity. Okay. So in this case, the velocity is higher here, and as A is small, and when the area increases, the velocity increases. But using this relation as well as the Bernoulli equation, this is the expression at the two sections. So we have this datum head expression of Bernoulli equation. So let's assume that there is no change in height of the flow. That means the earthing is a single streamline, as well as the height of the streamline is same. In that case, there is no change in potential energy, gravitational potential energy. So Z gets cancelled out. So from this, we know that let's say in this case, V1 is greater than V2. So if this is the case, we can if V1 is greater than V2, then this whole equation has to be equal. Then it is possible only when the P1 is less than P2. Okay. So from this equation we can know that whenever the area is greater, the velocity decreases at that point, and whenever the velocity decreases at that point, the pressure increases. That means the pressure is directly proportional to the area. So from this relation, we cannot judge that wherever area decreases, pressure increases. No, it is not inverse proportional. Basically, it is directly proportional. Okay. Now, as we have seen about the specific energy form, so we know the pressure energy, kinetic energy, gravitational potential energy, and the unit is kilojoules per kg, and they are represented in form of specific energy per unit mass. That is why it's a specific energy. Now we will see about the power form of the Bernoulli equation. So when Bernoulli equation for specific energy is multiplied with mass flow rate, we get the power equation form. So this is the specific energy form. When we multiply with the mass flow rate, we get such a form, and this form is called power energy equation, and the unit is kilojoules per second or kilowatts. So this is basically the fluid power, which is mass flow rate times gravity times datum head. So from this equation we can say that whenever the datum head increases, the power increases, and when the power increases, the velocity increases. Okay, so how to find the power form of the Bernoulli equation? Just multiply the specific energy equation with mass flow rate. Formula of fluid power. Fluid power is nothing but pressure times the discharge, and from this equation, power is mass flow rate times J times Z, and mass flow rate is nothing but rho times discharge. Which turbines are more efficient with respect to the power as well as the data? We'll see that. So, compressors, the flow is from low pressure to high pressure. For the turbine, the flow is from high pressure to low pressure. We know that. So we cannot judge how the flow will flow just giving the pressures. We will see that later, how to judge the flow direction of the fluid. So we know the power equation, rho Q G Z. So there are different turbines: Pelton turbine, Kaplan turbine, Francis turbine. So in Pelton turbines, the discharge is less, but the datum height is more. It means the velocity will be high. Kaplan, In this, discharge is high, the datum is less. In Francis turbines, discharge and the head are basically model. In Pelton turbines, as the datum height is high, the velocity is high. In this case, the less energy is generated, and these kind of turbines are basically used in Himalayan rivers. Kaplan turbines have high discharge, that means low velocity, low rotation, but the torque is very high, that means the energy generated is also high. Francis turbines are mostly used because it is used for moderate cases. Okay. So next, about the real flow. So Bernoulli equation are basically used in both. As we just discussed about the ideal flow case in which the fluid is inviscid, that means viscosity is zero. In that case, the datum head equation form of Bernoulli equation is this, and this part is called energy gradient conservation of energy. So in real flow, that is viscosity of the fluid has to be considered, and that viscosity effect is added here in the Bernoulli equation as HF, which is basically loss of friction head. Okay, you will see that. So what are the assumptions? What are the assumptions of Bernoulli equation? The first assumption is which parameter forever is steady flow, that means the velocity doesn't change with respect to the time at particular section, which fluid is an ideal fluid, which is inviscid as well as incompressible, and it is irrotational. If the real flow is considered, what additional assumptions are required? We will see that. But this is only for the ideal flow, but no friction terms are involved as the assumption is the flow is inviscid. So in the real case, the viscosity is, in the real flow, the viscosity is there, and the direction of flow can be estimated only through the real flow, not through the ideal flow. Okay. So in the real flow, the Bernoulli equation of the two sections are described like this. So in section 1, the Bernoulli equation is, and section 2, the equation is which is added with the loss of friction head. In this case, the energy gradient line EGL1 is greater than EGL2. So as the energy is lost due to the friction head HF. If the HF is greater than 0 at this point here, that means the direction is from 1 to 2. If it is less than 0, that means the direction is from 2 to 1, irrespective of the pressure change. We will see, we will just know about pressure change. So pressure change can be because of two things. One is because of the pressure changes, and the pressure change is due to the loss of pressure head. So the difference in pressure head can be calculated from the Bernoulli equation, pressure head form. So the change in the pressure is due to the change in area, given that the height are same. The pressure can change because of the friction head. Because of the friction, the energy reduces. That's why the pressure changes. So the horizontal pipe of the uniform cross section, given that the height is same, area is same, velocity is same. In this case, the continuity equation for ideal fluid, the pressure is same basically. So if it's in given case, we get a relation that is the height is same, that gets cancelled. The area and velocity same, that means these two terms will get cancelled, and we finally left with the change in pressure and the friction head term. From this case, we can get that the friction head is nothing but the change in pressure time divided by 4 times G. So from this information, we can know that using the manometer here, given these conditions, the pressure change through the what we calculate from manometer, we can see that the pressure is high at 1 and less than 2. From this thing, we can just know that the pressure is high here and low here. Okay, and the flow is from 1 to 2. Now we will see this. Okay, can flow travel from low to high pressure? Obviously, as you have discussed about the compressor as well as the turbine. So direction of flow can only be known through real flow. Yes, true. Known through loss of friction head. Yeah, as we discussed, if the in section 2 the friction is there and it's greater than 0, that means the flow is from 1 to 2. Okay, and about the we will see about this energy gradient line, hydraulic gradient line in coming section. Let's discuss about the application of Bernoulli equation. So first we will discuss about the venturimeter. So what are the components of the venturimeter? Venturimeter is nothing but a nozzle kind of structure with three parts, which is converging, throat, and diverging section. As you can see here also. So the questions are how to find the discharge using it, what is the coefficient of discharge here, if the venturimeter is inclined, will the formula change for the discharge, we'll see that. So there are three parts of this venturimeter. So the process of finding the discharge is nothing but to calculate the pressure change. So this is the structure, and the fluid passes through this throat part, and while fluid flowing through this throat part, we just use the manometer and use a different density, higher density fluid here to change to measure the change in height to, to, uh, to calculate this height. From this height, we can calculate the change in pressure. So the change in pressure, when we have the change in pressure value, we can find the average velocity. From this average velocity, we can find the total discharge. Okay, given that the height is c. The equation for the discharge is CD times A1 times A2, and this expression. And the coefficient of discharge is nothing but 0.98. We will see what does this mean, the coefficient of discharge. If the venturimeter is inclined, still the formula will be same, no difference. So the height h expression is basically nothing but times y. Okay, this y is nothing but this y. This is one mistake here. And using this information, we can find the total discharge from the pipe. And we will know about the efficiency later. Okay. Now let's discuss about the orifice meter. So orifice meter is something like this. You can see from this picture a small plate, a simple device. It's a plain sheet with the hole inside it. Like this. You can see the cross section here. And again, the manometer is used here with a higher density. And from this picture, you can know that the flow happens like this, and due to the uh, obstacles, the eddies are formed here in space, and the minimum cross-section area is not the cross-section of the plate, but it is this somewhat far away, a little bit away from the plate, which is called the minimum area found at vena contracta. This is the vena contracta place where the area is small. And the process of finding the discharge is to find the change in pressure and find the average velocity, and then we find the total discharge. And at vena contracta area, the velocity is maximum. And the coefficient of discharge is nothing but the actual discharge divided by theoretical discharge. And the coefficient of discharge represents the efficiency. If the coefficient of discharge value is high, that means the efficiency of that um, device is higher. Okay. So what are the questions? What is vena contracta? It is the minimum area where the velocity is high, and how to find the discharge, as we have seen. Find the pressure change, find the average velocity, then find the discharge. What is the coefficient of discharge? Nothing but actual discharge divided by theoretical discharge. So let's talk about the comparison of the venturimeter as well as the orifice meter. Which is more efficient and why? Compare the coefficient of discharge. What is its formula? So venturimeter and orifice meter. Venturimeter is costly because the fluid flow is much more efficient as the convergent divergence occur, and in this case the eddies are not formed. That's why the efficiency is higher, 0.8. In orifice meter it's cheaper, but eddies are formed, the energy is lost here, it's less efficient. That's why the coefficient of discharge value is less, 0.64. Okay. And let's talk about the pitot tube, a famous tube. So this is the pitot tube, you can see from here, and there are two pipes here to calculate the pressure. One is the piezometer and other one is the stagnation head. And this will get the pressure for high speed, high velocity fluids, because piezometer cannot be used for high velocity fluids, because for high velocity fluids the tube length has to be very high, but it's not practical. That's why we use bit of tube or manometer or say. But there are more facilities in bit of tube. Let's see what it is. So why is stagnation head higher than the static head? You see that. How to calculate velocity with respect to the device? What is the coefficient of velocity? Can we directly evaluate discharge with this device? How to find the average velocity? So we will discuss that. So this is the pitot tube here. The pitot tube finds the velocity at a given point of the depth. It's the instantaneous velocity at that point of the depth. Due to the velocity, the entire kinetic energy converts to the pressure energy, and that raises the stagnation. What happens is that at particular point when we have such a tube, due to the half mv square, the kinetic energy of the moving fluid, this energy is converted to the pressure energy, and that energy raises the pressure head more than the static head. This is static head. So due to that kinetic energy, which is basically pressure energy, that raises the head of this tube, and this raise is called the stagnation head. That's why stagnation head is higher than the static head. So the difference between the heads is nothing but the kinetic energy, v square by 2g, from the Bernoulli equation. It's not half mv square because there's no mass associated with it here. Only mv square by 2g is basically kinetic energy. So, and the velocity at that point is expressed like this, and there cv is nothing but the coefficient of velocity, and coefficient of velocity nothing but the actual velocity divided by theoretical velocity. Okay. So questions. Can pitot tube measure discharge? Okay, yes, it can calculate discharge, but pitot tube finds instantaneous velocity at the given depth. If the velocity profile is known already, then we can calculate the average velocity from that. If the average velocity is known, then the total discharge can be found. So as discharge is equal to area times the average velocity, and the average velocity is basically nothing but the maximum velocity divided by 2. You see the relation, how we get that. And average velocity is nothing but this expression from here. Where to put the pitot tube? It can be obtained only on the basis of the velocity program. Where to put? We'll see that later also. At which point to put, at which depth to put the pitot tube so to get the average velocity. How to calculate the difference between stagnation and the static head. So to get the difference, we have to create a manometer here. We have to link the piezometer and the pitot tube here like this, in a inverted U-tube or a normal U-tube like this. So there are basically, as we studied earlier, there are advantage of using inverted as well as inverted U-tube as well as normal U-tube. So you'll see that. So the height and difference is y, and to find the velocity we use this formula, and h minus small h is basically used as greater x. Greater x is equal to, as we have seen from the previous expression, density ratio minus 1 times the y is nothing but this distance. Okay. So when we for inverted U-tube, this formula is quite different, as the density used here is less than the density of the fluid flowing here. Okay. And these inverted U-tubes are used because it is very sensitive tube, and this is used when the velocity is less and it's changing frequently. And the normal U-tube is used where the density of the fluid in manometer is higher than the density of the flowing fluid, and this is used where the velocity is high. Okay. Next is the pitot tube efficiency with respect to the rotation accelerator. So if you rotate the tube at some degree, how does it affect? So it does affect when we move this tube between 0 to 360 degree. At between 90 to 270 degree, in this 180 degree difference, the static and the stagnation head doesn't change because the fluid is not entering the tube. But when we are turning away little by little, The fluid is flowing less. That means the less kinetic energy, less pressure energy. That's why less uh, stagnation raises there. What about the depth? When we use different depths, from this we can basically evaluate the velocity profile using different depths. For example, if we have let's say open flowing water, there's no cap on this, but the profile when we use this speedo tube like say a different direction, we will get a profile something like this, in which at the bottom where the friction is high, there the uh, velocity gradient is zero and it gradually increases at a certain point. But at the top, the velocity is not maximum because of the air force. Opposite air force, it creates the decreases the speed of the fluid on the top section. So the maximum velocity is somewhere like this here. Okay, let's see what are questions from here. So how is inverted U-tube and the normal U-tube used in pitot tube? What about the fluid density in H tubes? Under which circumstances are they used? Formula, we have discussed all these things. Formula to calculate the velocity, it is discussed. Formula for differences in stagnation and static height, we have seen it. Formula as well as for the inverter and U-tube also. So rotator P-tube. How does the stagnation height differ with respect to the rotation angle of the pitot tube? We have seen it. How does the velocity vary with respect to the depth of the tube? We have seen it in motion, as we have seen in this case. So, questions. So, what is the comparison between the Venturi and the office meter? So, which is motivation with respect to the coefficient of discharge? Compare the volume of discharge and what is the formula? We have seen it already. So, now let's discuss about an important topic called Navier-Stokes equation.